Waste of gigabytes.
Oh, we're almost done. Where's that gone? Here yet?
Functional and structural changes? Maybe not.
Did we just start it?
No?
This stuff here, the classification.
Right here. Right here.
Hold up, hold up, hold up, hold up, hold up.
Did we do incidence and prevalence already? We did that already.
I have mine all mixed up.
We did incidence and we did portal elementary.
After extent of host.
Which one?
Extent of host enrollment. That's the last slide I have.
We did that.
We did that.
I don't remember any of this.
I did this, I talked about the scientific design, yeah.
Huh?
We missed Friday.
Oh.
I think you did that also.
Who did?
I think it's
I think it's here, right? Yeah, I did it, yeah.
Why?
Did it both of them.
I was
Yeah, I did.
honestly.
I don't remember that slide either, but I put it in.
That was just like bye.
Okay, there we go, that makes sense, I put that in. All right. I got a little bit more of my stuff. Okay. So, these things then post involvement. Let's talk about bacteria, and I'll go up to sepsis in a minute. So that's a major cause of mortality in hospital in sepsis. That's probably one of the main ones. Okay? So, bacteremia, so don't look at that. Bacteremia is just the presence of bacteria in the blood, right? It's not doing anything, it's just in there. It's not dividing, it's not really metabolizing much, it's just in there. Why would that be a problem? You've got some in your blood all the time. Your liver is constantly getting hit with bacteria that sneaks in through the intestinal system. That's one of the problems with proton pump inhibitors we'll talk about later on.
Can it spread?
It could spread. That's the problem. Is it may not be a problem right now, but if it goes somewhere where you don't want it to be, like say the heart, you get into carditis or something like that. So bacteremia is not good. Septicemia is also known as what they call blood poisoning. That's kind of the old school term for it. You ever hear the old tale that if you get a cut, you start seeing red streaks coming up your hand, that you've got blood poisoning? Okay, that's septicemia. Septicemia is the presence of bacteria in the blood, but it is actually growing and dividing and metabolizing and producing toxins potentially. That's a huge problem because that's going to elicit a what? An immune response.
So bacteria is not growing.
No, they're just going on for a ride.
So that's the red streaking then, right?
Yeah, so you get inflammation and stuff like that. So you're triggering an immune response. Okay. What's toxemia? It's not on there. Toxins in the blood. So if you were to get a toxin in the bloodstream, that'd be toxemia. So write that down on here, on your thing. It's not on there. Sepsis, a lot of people kind of think is, they have the common thought of what sepsis is tends to be wrong. It's not septicemia. It's nothing to do directly with the bacteria itself. It's the immune response to the bacteria. So sepsis is a toxic inflammatory condition arising from the spread of microbes, especially bacteria, or their toxins. So septicemia, right?
What?
From the focus of the infection. So you get a cut, right? You get the damage, you get whatever. Bacteria gets in your bloodstream, starts dividing, starts multiplying, starts releasing toxins. You do what? You initiate a massive inflammatory response. And that's what sepsis is. It's an over-response to this condition. And it systemically. So you have this massive inflammatory response. And that inflammatory response starts damaging all of your organs.
So is that your immune system starts attacking?
Yep. It's an overreaction to this. That's why it's so hard to treat. How would you treat sepsis?
Anti-inflammatories.
Nope.
Anti-inflammatories.
You can do it, but is it really directly? It's already too late.
Yeah.
Half the time when you're in the hospital, it's too late for the antibiotics. You're already gone septic. You already got sepsis.
Anti-inflammatory.
What anti-inflammatory does? Think about it. I mean, you're right. You're trying to shut down the inflammation, but what, ibuprofen?
No, like maybe even antihistamines, some sort of like something to.
Main thing's going to be steroids.
Oh.
You're going to try and put somebody full of steroids. You're going to try and tone down this entire immune response as fast as you can. The problem is, it just doesn't work that well.
Yeah, isn't sepsis like,
Where did you
you're gonna
work
die?
on something like that where the cytokines with AIDS? Like with that targets inflammation pathways?
With AIDS?
Like a medicine that's like AIDS?
I don't know if it's with AIDS, but it was for AIDS to treat inflammation.
Well, mine, yeah. I mean, anytime a cytokine, because, okay.
Uh-oh.
One of those tangent headaches I get. Okay, so now we're going to go off on a cytokine. What are cytokines?
They're like mediators or like chemical messengers, I mean?
Of what, though? Are they like hormones?
No.
They're chemical messengers, or they're signaling molecules of the immune system. Mainly cytokines, right? So they orchestrate the immune response, chemically signaling. Macrophages, T cells, all release cytokines to rev up this response. So write this down because you open the doors and now it can be on the test.
Oh God.
you know what?
You
Cytokines.
can have pro-inflammatory cytokines or anti-inflammatory cytokines.
And cytokine is with a C, right?
Yeah.
Cyto.
Cyto,
Anti-inflammatory?
yeah, pro-inflammatory and anti-inflammatory.
Because like pro.
Which makes sense. Some of them rev up the immune response. The other ones do what?
Stop it.
Lower it down. So all I can think of what you're talking about is they're trying to reduce the inhibitory cytokines to try and tame down the immune response. When we get to inflammation later on, we'll probably talk about it, but we'll bring it up right here. The problem with chronic inflammation is what? That's a huge issue now they found out. Diabetes, cancer, metabolic syndrome, all these are due to what?
Inflammation.
Chronic low-level inflammation. And the problem with that chronic low-level inflammation is you have this chronic low-level release of these cytokines, so you're keeping that immune response constantly what? Turned on at a low level, but you've got this inflammatory response, which causes damage.
So when it's sepsis, it's rapid and it's
When it's
hard
sepsis, you have this massive release of these cytokines, and somebody even call it cytokine storm. You have this massive release of cytokines, and you just rev up this immune response so powerfully it starts just damaging everything else, in particular your organs. So you get massive internal organ damage, and they usually die from multi-organ failure.
and there's no, pretty much nothing.
They do. They try and pump you full of steroids to shut down that inflammatory response. It's sort of hit or miss. It's not like you see it coming, bam, you can try and do it. They're actually trying to look at tests now to see what might be causing it before it happens. Type thing. Can we pick this up before it gets too bad?
Yeah, because what I remember about it is it's not FDA approved, but there's tons of, because when AIDS came out, they were trying to do, I think it was with AIDS, but they were just doing very unexperimental stuff.
Oh yeah, they're trying to do anything they try to do when it first came out. I think I do remember something. I think you should talk about it. I think there was an attempt because HIV attacks the T cells, right? I think what they're trying to do is they're trying to slow down the proliferation of the T cells to try and starve the virus of targets. I think I remember something like that, but that was a while back. Can't breathe. All right, just remember this one right here. Know what sepsis is. What is sepsis?
Overreaction to
Good.
infection.
And it's right down. There's tons of research on trying to get rid of trying to mitigate sepsis because it is a major cause of hospital deaths right now. It's
That's what the flu, right? We died from sepsis.
what do you usually die from the flu? What's the main
Pneumonia.
cause? Pneumonia. Usually pneumonia. Usually you get, because you've already got that irritation of the lungs, and so now you get bacterial pneumonia, and usually it's in the elderly, right?
So is sepsis, is it only bacteria that toxic?
Mainly. Not only, but especially bacteria. It can be anything.
That causes an
Any microbe that triggers that immune response can cause sepsis. But it just tends to bacteria because they're going to be growing and dividing and releasing a lot of toxins and stuff. Because remember, how do viruses kill cells? They get inside, they grow, they kill the cell. Bacteria actually release toxins and things like that. If you're gram-negative, you're going to have LPS, which is a massive inflammatory response inducer. So, generally bacteria. All right, disease, course of infection. I'm just going to skip these right here because we can all read right here too.
Okay.
Incubation period is what?
The time it takes for symptoms to appear?
Which is kind of getting to colonize.
Once you've been infected, once you've been contaminated, get infected, the bacteria starts to get a foothold of the virus, but there are no signs or symptoms, right?
Yeah.
Prodromal is that vague general symptoms like I talked about in microbe. To me, that's when people are like, I feel like I'm getting sick. You know that feeling when you feel like I feel right now? I'm in a prodromal phase, I think. I hope I'm not, but I feel like it. That's what it is. I feel like I'm getting sick. I'm coming down with something. Illness is bam, you're sick, right? Most of their signs and symptoms: fever, headache, malaise, lethargy, chills. What else? Oh, I'm forgetting there.
Well, that's the acute stage.
Muscle ache. Yeah, this is going to be the very acute stage. And then declining, obviously, as you're starting to get better, but you still feel what? You're still sick. You still can have a lot of symptoms and stuff, but they're starting to go away. Everybody knows that one. Convalescence, you don't hear much anymore. They don't use that term much anymore. They used to have convalescent homes and stuff where people would go, especially the wealthy, when they were sick. I don't know. They spent like 6 years there, so I don't know what they were convalescing over. Convalescing, though, is when you really are done with signs and symptoms, but you haven't completely eliminated the pathogen out of it. But your immune system is kicked in. And this is actually what's happening to your immune response as you go through this.
It's activating.
So here you're turning on your immune response, it's at full blast, because what causes your signs and symptoms? Is it the pathogen? Is it the bacteria? It's the immune system, right?
Mm-hmm.
So after this, your immune system's kicked in, you're starting to look at what? The number of microorganisms starts to drop, and what also starts to drop? You start attenuating your immune response, right? And this is another from one of the other books. But here you've got infection, right? And here's the incubation period, and here's your prodromal phase. Like you were talking about being acute, this is going to be an acute condition. Acute condition is going to be what? You're going to hit this threshold, that critical threshold. Well, we don't want to kill anybody right now. That's if you don't make it past that. That's death. But this is going to be critical threshold. That's where your immune system is fully kicked in. You're feeling the sickest you are, and you should start doing what? Getting rid of it. So now your signs and symptoms are going, but what? Number of pathogens start to do what? Decrease. Start to disappear unless you have a chronic disease. You know, chronic disease, what's happened here?
Contact. Constantly.
You don't completely eliminate whatever the condition is. In this case, let's say it's chronic sinusitis. A lot of people have, right? You're never getting rid of. That's good English. You're not completely clear the what?
Virus.
The organism, right? So you have a chronic disease right here. And you're still above what? What's clinical threshold?
The amount you need to be considered like sick or?
That's not considered to be death, too, no? Like super sick.
Well,
That's
clinical threshold is where you actually start exhibiting clinical signs. Yeah. That's up here. That's where you start going like this. They're cute. It's like, and you just keep going. Well, you don't keep going, you stop going, right? Because you die. But this one, it gets that bad. Clinical is going to be where you manifest signs and symptoms where you have clinical disease. Subclinical is going to be what?
Not sick.
Let's say I picked up the cold from one that's going around, but I just didn't really get what? Sick. So you can have what's called subclinical disease. How many people here have been exposed to herpes simplex 1?
Everybody.
Pretty much everybody. A lot of people have what? Subclinical disease. They will have it, and they will never ever get an outbreak from it. But they still have the infection, and if they get tested for it, they're going to test positive for it.
So
But
that
you
would be
never.
considered like the what's the word, covert?
Well, it could be a covert. I've never used the term covert before. Because,
I think it was,
oh, it did.
that requires laboratory testing to detect.
Yeah. Okay. Yeah. Yeah. That's a word. Yes. So if it's not clinical, if it's subclinical, you can't detect it by signs and symptoms. The only way you would detect it would be what? Laboratory test, imaging, something like that, right? Then there's that convalescent, and then finally you should get what?
Resolution.
Resolution when you clear the entire pathogen from you. I get sick this. I would get sick on the weekend too. Ridiculous. All right. Type factors that influence the site of the infection is going to be the type of pathogen, especially viruses, right? Portal of entry, how is it going to get in? And the competence of the host immunological defense. A lot of times we're exposed to stuff and we never even what? Never even know, right? If you're immunocompetent, you get an opportunistic pathogen, you may not even know you're exposed. You may have subclinical disease, you're going to get it, it's going to try and take a hold, but bam, your immune system's going to kick in. So let's go through these one a minute. Is the following statement true or false? The symptoms of an infection are always obvious and apparent.
No, false.
Can you go back one slide though?
No. I'll learn to write that.
Okay, well.
You got the video, don't worry.
Okay.
False. Symptoms may be covert, there's that covert word, and non-specific in presentation. That's kind of weird though. What's your own opinion on this right here? The symptoms of an infection are always obvious and apparent.
Covert, isn't that like they're hidden?
They're hidden.
But that's like a weird word.
It's only in the laboratory.
Yeah, well, yeah, it's
That's
kind
the
of a,
definition of the book.
yeah, it is. It's a new one. I think it's a weird word because to me, covert
Like hiding.
is like hiding, but it is hiding. And it's just another way to get through there. Whoever decided they got to change the wording every once in a while to keep their job, right? Somebody's got to change stuff, otherwise there's going to be no more job. But to me, what is a non-specific presentation of a symptom?
When it doesn't.
When your symptoms can be mistaken for something else because they're so
What's non-specific? What's a non-specific?
Not
general.
Cough.
Like a fever, right?
A fever, a cough, malaise, things like that. But to me, those can be pretty apparent though, right? They're just, they call them non-specific. A
like
sore throat.
obvious, you mean?
Yeah, they're obvious. They're apparent, the patient. Symptoms are subjective feelings by the patient, right? So if this is saying symptoms of infection are always obvious and apparent, and it's saying false, then it's saying they can be non-specific in presentation. I don't have the wording on that, because non-specific just means you're experiencing a symptom, you just don't really know what it's causing it, right?
That's like the idiopathic.
Kind of like, except this is a symptom, not a disease, so.
Okay.
So,
But still.
yeah. So this would be, I don't like that word. All right. I want to go through these. Which one of these does antibiotics fall under?
Antibacterial.
Good. Thank God nobody said antiviral. Antibiotics in general vernacular are talking about antimicrobial drugs, in particular antibacterial drugs. Antiviral agents go after
Viruses,
Antifungal agents go after? We're
funguses.
pretty tricky here, guys. The last one, antiparasitic. Okay, those can be broken down into antiprotozoans, anti-amoebics. If you have an amoebiosis, what's amoebiosis?
A lot of amoebas? I don't know.
What would amoebiosis be?
Too many something.
Osis.
It's infection with amoeba, you got it?
Yeah.
Amoebas
Well,
are
not too
everywhere.
many, there's a bunch of amoebas out.
Well,
Real
amoeba-
Grand, Real Grand doesn't have amoebiosis. Amoebiosis is an amoebic infection. So you can have anti-amoebic, so I'm just saying,
Are they
antiparasitic.
toxic though, antiviral?
Well, there's a good question. What is the why? Okay, why are there 900,000 antibiotics?
Because they're easy to treat.
If you could think of that class, there's good selective toxicity. We are not prokaryotes; they're prokaryotes. So they have cell walls we talked about, right? Wait a minute, am I just discussing the whole rest of this chapter before I get to it? Okay, I'm not, okay. So, there are a lot of targets they're what we call druggable targets in bacteria that aren't gonna affect us. We don't have cell walls. Almost 50% of the antibiotics target cell walls. Their protein, their ribosomes are different shapes, so about another half of them go after their ribosomes, things like that. They're easy to target without being toxic. Viruses hijack our cells, so can you just shut down protein synthesis in general to stop a viral infection?
No.
No, you would kill
You
what?
shut your own good cells.
Kill the patient, okay? Can you shut down DNA synthesis or transcription globally?
No.
Again, no, because you just killed the patient again. So you've got to have a target that's only going to affect the virus. You can target some of the mechanisms and the enzymes inside of people that they hijack, but those tend to cause side effects. So a lot of the anti-HIV medications in particular, when they first came out, had lots and lots of what?
Side effects.
Yeah.
Lots of really bad side effects. That's why there are very few antivirals. They're very expensive. And you notice too, they only target
So
what?
they're still
They
not
inhibit
safe.
the reverse transcription.
No, they're getting them a lot safer. A lot of them a lot. Well, now the anti-HIV medications used to be you took, let's see,
Like
a
5
friend of
different
mine
pills.
who wouldn't even eat because he was taking like 30 pills like 3 times a day or something like that. Now it's down to 1 pill a day. So it's not that bad. They made them a lot better stuff. The ones that are really hard too are these suckers right here.
Because they're closer to our cells.
Antifungals until recently were all incredibly toxic.
What are types
This-
of like fungal infections besides like feet and stuff like
I'm
that?
trying to explain, hold on, one last time. Systemic ones were very toxic until recently. Antifungal. No, I'm sorry.
What are type of fungal infections like besides like feet?
Leptomycosis, coccidioidomycosis.
Women can get
Hmm?
other areas. Women get fungal infections.
Yeah, those are gonna be more yeast infections are gonna be and dermatitis, dermatophytes. Those are all gonna be more-
Dermatitis is a type of fungal infection?
So, well, type of dermatitis, it is. Dermatophytes can cause it.
Oh,
So
okay.
they're not systemic though.
They're not systemic, so they're topical. So those are easier to target. It's the systemic ones, the blastomycosis, coccidioidomycosis, the Rift Valley fever. Weren't we talking about that in San Joaquin Valley fever in here? Those are all really tough to treat because they're systemic. And they've gotten some better drugs now. Don't get me wrong. Now they're a lot better. Back in the past, they were incredibly toxic. Antiparasitics really aren't too bad, really. Kind of weird. All right.
Isn't the only danger with antiparasitics is killing them too fast because of the
Right.
immune response?
What happens, a lot of them, they cause the parasite just to die,
Which
And you
reduces
kill
toxin.
and you get a massive what?
Immune response.
Massive inflammatory response.
Oh, wow.
So that's the problem with it. That's why for a long time, oh, I'm not gonna do this, I'll get in trouble.
Uh-oh.
I don't want to get sued. All right. I should take it as BS, but anyway. Bacterial resistant mechanisms, inactivation of antibiotics. The main one out there, okay, I'm going to go on this real quick. The penicillins and stuff, the ones that stop cell wall synthesis, are called beta-lactams. And they inhibit, so the cell wall is like a brick wall. They prevent you from cementing the bricks together in the bacteria. So as the bacteria grows, the cell wall gets weaker and weaker and weaker. And it eventually lyses open.
So it's an enzyme you said, beta-lactase?
Beta-lactame.
Team.
Now, inactivation of antibiotics, the ones that become resistant to it make an enzyme called beta-lactamase. And that enzyme inactivates the
The
beta-lactame antibiotics. So that's inactivation of an antibiotic. Genetically altered antibiotic binding sites. So if you're going to have that enzyme beta-lactame, that drug's going to bind to a particular enzyme, you just change that enzyme a little bit and now the beta-lactame can't bind to it. Bypass antibiotic activity is a lot of those sulfa drugs. The sulfa drugs competitively inhibit one of the enzymatic pathways to make DNA and RNA. So the sulfa drug shuts down that pathway. That means the bacteria can't make what? DNA or RNA. If you can't make DNA, you're going to what? You can't replicate, right? You're going to die. Okay? What they do is they just bring in, so you've got, you've got PAVA,
Oh yeah.
which goes to I'm not going to spell it out. Dihydrofolic acid. Dihydrofolic acid, which gets turned into folic acid, which gets then eventually down this pathway gets turned into DNA and RNA, right? The sulfa drugs block this pathway. Okay? So you can't turn, the bacteria can't turn PAVA into dihydrofolic acid. That means they can't make what?
Yeah.
RNA or DNA. What the bacteria do is say, fine, go ahead and do that all you want. I'm going to bring dihydrofolic acid in from the environment, and I'm just going to skip that whole pathway. So will the drug do any good? Changes in the bacterial cell wall. If you change the way it works, then the beta-lactams aren't going to work. You can also increase the antimicrobial transport proteins that pump out the drugs. All right, maybe I'll give you a list of those later on. You can look up.
Yeah, that'd be great.
Antiviral mechanisms, these are going to be different. These are the antivirals themselves. There's just the nucleoside analogs and protease inhibitors are the two main classes of drugs. Nucleoside analogs look like the nucleosides that go into the DNA and RNA, right? But they don't let that chain, they don't let you keep adding on the new nucleotides. Y'all remember DNA synthesis? Y'all better. You guys are way up here. It goes what? You add a new nucleic acid to a new nucleotide to the bottom of the chain, right? And the DNA grows.
Mm-hmm.
But you have to have that man, ready for the weekend. That free 3' hydroxyl group, right? To add that 1,2. If you don't have it, okay, I'm not sure. I'm getting some looks like I have no idea what he's talking about. So
Does
this,
it have a sugar also?
yeah, it's actually on the sugar. It's on the 3' hydroxyl group on the sugar. So here's that sugar. That DNA or RNA.
That has the sugar? Would
Well,
be-
they both have sugar. One's got ribose, one's got deoxyribose.
RNA.
Come on, quick.
RNA.
So this is RNA?
No, that's
Deoxy.
deoxyribose?
Yeah.
That's DNA.
This is DNA?
Yes, I don't know. Yes.
That's RNA right there.
Oh, it's RNA.
That's
Is it
RNA.
I know
RNA?
one has one less sugar than the other.
So when I said RNA, why didn't you say yes?
Because I'm like, no.
No, second guessing.
But you should know. No. All right, we'll go over that later. I'll review guys that on the later. That shows up. But right here, this 3', you have to have that 3' hydroxyl group. Everybody remember that. Okay. Because the next one, that's where that phosphate group is going to come up and make that phosphodiester linkage, right? What nucleoside analogs do is they'll get rid of this and they'll put a nitrogen there or something. So when the virus is trying to make its DNA or its RNA, can it make it?
No.
No. So that's what nucleotide analogs do, nucleoside analogs. Protease inhibitors inhibit the viral proteases they need to make all the stuff. Their enzymes, because they carry information to make their own
It
enzymes.
just slows down the.
Just shuts down, yeah. So let's say
Without that enzyme,
they can't make their components to make the rest of the virus, so they shut it down. These are the main two ways right here.
So when it's resistant.
Shuts down the enzyme or shuts down what?
It shuts down the enzymes, the
protease is
proteins.
enzyme.
It inhibits whatever enzymes or proteins the virus needs to replicate. Okay, so now you.
How about the reverse transcriptase?
That's the last one, reverse, okay, but that's only for HIV and retroviruses. So that's a transcription inhibitor, but it only works on retroviruses. Y'all remember what he talked about that? HIV is so bad, retroviruses are bad, why?
Because they attach to your DNA. They get inside.
They integrate they reverse transcribe the RNA into DNA and it integrates into your DNA. Once it's integrated in there, it's there forever.
Mm-hmm.
The enzyme called reverse transcriptase that does that. That's a nice target for retroviruses because we don't make reverse transcriptase. You inhibit reverse transcriptase, it can't integrate in there, right?
Mm-hmm.
But that's so specific, I think that's why they left it out here. Although these are the big ones for HIV too. So the need for combination of or altering therapy with multiple antiviral agents. The reason they do this is even if you're on a couple nucleoside analogs and a protease inhibitor, HIV, how many copies of HIV make every time it replicates in a cell? How many copies of a cell does it make?
Thousands.
millions, right? I mean, you look at a drop of blood, I've forgotten how many million viral particles are in a drop of blood.
Sheesh.
So there's huge amounts of these things. But HIV its polymerases are very sloppy and they don't proofread. So they make a lot of what?
All bad ones?
They make a lot of mistakes.
Yeah.
So if you make a bunch of mistakes when you're trying to copy your virus, and you've got 1 million copies,
So there's gonna be a lot of inactive ones?
hold on.
Oh.
That's a million. You want to add 2 million? Well, let's just make it a billion. You're making 1 billion copies of yourself, right? If you make a mistake in 500,000 of them, and they don't work, do you care?
No.
But one of those mistakes might make you resistant to one of those drugs.
Oh.
And that's why it became resistant so fast. It makes so many mistakes that just randomly, out of the blue, one of those mistakes made it resistant to this drug.
Wow.
So if you put them on 2 or 3 drugs, what are the odds of any one virus that replicates being resistant to all 3 drugs? Very small. And very,
Yeah.
the chances are almost minuscule they would ever do it. Because it'd have to be that same virus. You couldn't have 3 viruses become resistant to each one because then the other drug would kill it, right?
Yeah.
The same one virus has to become resistant to all 3 drugs. And the odds of that happening are very slim. Now, it does happen. So these people have become resistant to it. It's incredible. But that's why they put you on the it's called
A cocktail.
HART. Highly active antiretroviral therapy. It's at least 3 drugs, I think they put you on now.
That's for HIV, right?
For HIV, yeah. All right. Man. All right, here we're talking cytokine therapy. Here you go. So supplementing or stimulating the host's immune response so that the spread of pathogens is limited or reversed. The idea behind this, before they came up with these new immunomodulating drugs, was if you can't cure this, maybe you can stimulate the patient's immune system to go after it. You can give it a little bit of a boost. Okay? Because I don't say 100%, eventually your immune system can usually what?
Fight it off.
Can usually catch up after things, even rabies, they can get it. So I put interferon alpha, interferon A, and hep C. Why do I have that on there?
A helps boost the immune system.
It helps boost the immune system, in particular, what part of the immune system? Anybody know?
Well, that's reducing the growth of cancer cells, right?
This is looking for virus, but this is interferon.
In the liver?
Actually, it helps boost the.
Well, the leukocytes.
Well, it actually turns on the antiviral mechanisms in all the cells around it. That's what I'm do. So when a virus infects a cell, right? That cell is done, right? But it can start telling the other cells around it, there's a virus out here. You need to turn your alarm system on.
Mm-hmm.
So interferons do that. That's one of them they do.
Turn
And
on.
there's cancer stuff too. But one of them they do. A lot of these cytokines have multiple pathways they interact with.
It's
Do you inject one with it, or do you give it to your interferon?
Yeah, before they came out with the drugs for hep C, the only treatment was riboflavin and, not riboflavin, it's a B, rifampin, jeez, and interferon. And the idea is they put you on this interferon and hope that your immune system would clear the virus. And it worked about 30% of the time.
and that's just to boost your immune system.
It just turned on the antiviral things. The problem is, like those pathways I talked about, they turn on lots of pathways, and this is a pro-inflammatory cytokine, so what happens?
Immune response?
Well, what happens to the person?
Shock?
Nope.
When what?
So this is a pro-inflammatory cytokine. Turns on locally, it turns on the antiviral response in the cells. Systemically, it's pro-inflammatory.
Oh,
so
it
what?
would make you turn on yourself, right? Or
Not
no?
turn on yourself,
Turns
huh?
on the inflammatory.
Turns on inflammatory response so you feel like what?
Shit.
Yeah, well. The problem with this therapy is you were on it for about a year, and you just felt like you almost, the guy I knew had it, said he felt like he had the flu for a year.
Wow.
Almost. Not quite as bad, but that was the problem with it. So compliance, which is the worst problem you guys are going to run into, what is compliance?
When they don't
They don't listen to you.
They're going here to their drug therapy regime. Ugh. So that was the big one. Pathogen-specific antibodies given to the patient as an infusion to facilitate neutralization. phagocytosis and clearance of infection agents above and beyond yeah.
I'm not even gonna write that down.
When did they just use this? What is the best example of this we just saw 2 years ago?
The flu, what is it?
Clearance of
No,
infectious
it's called
Or the
passive artificial immunity.
passive.
Hey, you people that micro with me, you're all in big trouble right now.
I don't remember you
No,
going
you
over
didn't.
that.
You were in the general micro. You're doing
Yeah.
micro disease.
Is that-
You're fine.
Is that when we were talking about how the donor poop, like
Anybody remember what it is?
The donor what?
poop, like
Oh, the pill? The pill?
The poopy pill?
yeah.
Oh, that's
Wow.
different.
What are you talking about?
I was thinking that because it's
This is antitoxin, immunoglobulins, gamma globulins,
Oh, the rattlesnake.
rattlesnake.
Oh,
venom.
rattlesnake.
It's when they take the antibodies from an something they infect that generates antibodies to the pathogen and inject them into the host. Ebola was the last time this was used clinically. Well, no, it's used clinically all the time. Ebola was the last time you saw it in the media. What happened to the Ebola nurses that came over?
they got
They
that.
gave the doctor the last medicine, right?
Yeah,
They gave the doctor the last medicine.
But they took his antibodies and put it in them.
Because he made antibodies too, and they take the antibodies, they took the antibodies out of the doctor who cleared the infection, and they inject them into the nurse.
Was that one guy where they only had like it was like 3 pills?
Yeah.
Yeah.
And they gave it to that one guy. So, but actually, the first ones to really do that were one of the first outbreaks were the African physicians. They were the ones who a bunch of the WHO physicians weren't going to let them do it. And one of their colleagues was dying, and they just basically gave the WHO the finger and did a transfusion with a patient who survived Ebola and saved a whole bunch of the patients. So. But it's been going to do before they had. You guys have all been vaccinated against Hep A, right? Mm-hmm. Before you had the vaccine for Hep A, the treatment was gamma globulin. So they would take a patient who'd gotten over to Hep A, take out an antibodies, keep them real cold, and if you got Hep A, they'd...
Was it real bad, I think, before?
No, I wouldn't, it's not that. It can kill some people because they can rupture their liver. But the problem with Hep A, the symptoms of Hep A was your liver got like this big, so you got hepatomegaly, and then you got jaundice, usually real bad, you got sick. But most people didn't die from it. I had a guy in high school. I had a lot of friends got sick.
You have some good stories.
All right. The recovery of a probable pathogen or evidence of its presence from an infected site of a diseased host. So criteria for diagnosis of an infection, accurate documentation of clinical signs and symptoms. This is symptomology. You can use symptomology to help what? Diagnose, right? In fact, most diagnosticians, they used to use a lot of symptomology. Before you had CT scanners and MRIs and PET scans, what did you have to do? What were the old, and it's not that long ago.
Write down the list of symptoms and try to figure it out.
They were called diagnosticians, so they used what was available to try and diagnose disease, usually looking at signs and symptoms.
So is this how the moms that have Myers syndrome and they get their kids to have all kinds of unnecessary surgery?
Oh, so you ever heard of that one, guys?
Yeah.
Well, there's two of them. It's called Munchausen syndrome.
Oh,
Which is where
Munchausen.
Munchausen, where you are constantly faking disease.
Like where you think you're sick all the time.
No, that's
That's
hypertension.